So today I'm going to talk about Agile analytics applications with Hadoop. My name is Russell Jurney. I am a data scientist. I live in Pacifica. A little bit about me. This is like last year, the year before's world bearding champion. I'm trying to beat this guy. Bearding is my natural talent, I discovered. I'm probably better at it than anything else. I'm going to be giving away a few copies of Agile Data Science, the book, for good questions afterwards, so pay attention. If you use this code at O'Reilly, auth-D, you get like 50% off. So we go fast, but don't worry. If you Google me on the Hortonworks and Data Syndrome blogs, there are examples for like everything we cover with code on GitHub. So in terms of application development, building web apps is a fairly mature venture at this point. Like since Rails happened, there are all these post-Rails frameworks, and you can use an Agile methodology and set out to build a web app and have a pretty good chance of building something that's going to be useful to someone. It's a pretty mature field. And then you have data warehousing, where you have data warehouses that satisfy business intelligence requirements, but they tend to be fragmented. And so you can never get at the data you need. There tend to be very complicated processes to get like new tables added or to do the joins you want to do. So data tends to be segmented. And then you've got high performance computing or scientific computing. That's UNIVAC and that's Deep Blue. They sort of have similar architectures and look the same. They're both warehouse scale machines, just of different eras. This is like MPI, Globus, Smart Kid only technologies. I tried to use them like in college, and I couldn't figure them out. Like word count was really hard. And so you might define data science as the intersection of these three fields. So now we got these warehouse scale machines, but it turns out it's very hard to utilize them at scale, all the different commodity machines together, because of the disparities in speed and capacity of local RAM, local disk, and network. And so like Hadoop to the rescue. It's really easy to use, especially as compared to like MPI and these other platforms and frameworks. There's Pig, there's Hive, there's cascading, it's high-level interfaces. It's incredibly cheap. It's about 1% of the cost to use network-attached storage as compared to network-attached storage or a storage area network because it's local disk. And so an apartment can buy its own Hadoop cluster without having to get like overhead approval. And so what you end up doing is dumping all your data from all the data marts and data warehouses and applications into one place. Hadoop forms this data lake. So you start doing joins that you've never been able to do before. People become nocturnal. That way you can have the Hadoop cluster all to yourself. It's a pretty sweet thing. You can do all kinds of ETL. You have an army of mappers and producers at your command. So once you've got this, now what? What new opportunities does this expose? And so it's the analytics application, which is to provide insight, make predictions, predict the future. So to build these things, it's a very broad skill set from customer representative through marketer, product manager, interaction and experience designer, web developer, or hardcore researcher. Nobody has all those skills. So they told us this in film class. Making analytics applications is inherently collaborative. So it's a team effort, no matter what. And so a data science team, ideally composed of 3 to 4 people. If you have more than this, communication overhead tends to override and start to be very costly. You can have expert researchers in your organization, and you can sort of use them as resources and whatnot, but you generally want T-shaped or generalists on a data science team. Treat it like a creative studio, not an assembly line, where you do have hardcore deadlines and requirements, though. So what you want to do in an analytics application is get insight into a product. But how do you do that? So this backend now has gotten really thick. Hadoop is this entire other thing that sits behind your database. So generating insight that people would pay for in an analytics application can take like 10 to 100, even more time compared to skinning that application, for the web. And so there's this timeline disjoint of doing analytics or hardcore research with data versus building agile web apps or mobile apps. And so how do you ship insights efficiently? And how do you collaborate on these two different timelines, the research timeline versus the application development timeline? So there's definitely a wrong way to do it, and that's to kind of bolt it on to your existing process, where it's like, oh, we made this great design. Your job is to predict the future for it. You're a data scientist, day one. Hey, what's taking you so long to reliably predict the future? Okay, well, you made a really accurate model, but the users don't understand what 86% true means. This would come up on Flightcaster a lot. Your flight is 86% on time. I sort of understand that it's like inference, but like my mom definitely doesn't get that and is angry whether the flight is on time or late, depending on what she expects. So you're freaking out, and the plane has hit the mountain. Kind of reminds me of the waterfall model of software engineering that we all got away from because it didn't succeed very often. And so there's a big problem. You can't design insight in analytics applications. You can't specify this up front. It doesn't work that way. You have to discover insight, and you discover by exploring. So that we might formulate a strategy that's to make an application for exploring your data, where you iterate and publish intermediate results, and that becomes a palette for what you ship, whether it's an application or a system or an API. And so there's this concept of data design that takes into account the fact that it's never the first query, it's the 15th to the 150th at 2 a.m. that gets those aha moments. And it's slow to do those in batch, and any system with a large amount of data, they tend not to be instant. But more than that, if you had a SQL prompt and you do have a big data warehouse and you can query it, the context of the insights that produces is not very good as compared to like a web application that's properly contextualized for the user experience that you're after. So it's actually easy to also invest man years in the wrong statistical models where you define a problem slightly off and you have a researcher that does exactly what you asked, and in the end you get very little use out of it. I've seen this happen. Like pre-designing charts up front, we're going to do this chart and that chart and that chart. The charts end up being boring. They often get pushed to the back page. And then the semantics of presenting predictions like 86% true, those are really complex and subtle, and it's the core of your application. And so you really want your designer and your data scientist collaborating on that presentation from the beginning and throughout the project, and not like the day after you ship when people don't understand what 86% true means. And so the core opportunity lies at the intersection of data and design. So given all that, how do we get back to agility? So a statement of principles and then tricks with code. So we want to set up an environment where insights are repeatedly produced, where they're shared with the entire team, where your application is interactive from day zero, where your data model is consistent end to end, so that everyone can understand the data as it exists and work with it on a reality-based level, as opposed to sort of mock-ups or something like that. So that you want minimal impedance between layers so that anyone can publish up to that next layer with one line of code. And then the insights that you generate during this process is the palette for what you ship, hopefully until the application pays for itself and more. So here's like a snowballing publishing audience chart. You want to share the research at least weekly. Even if it's not done, you can share something intermediate with the team and get that pushed out into an app. That way everyone understands what the process is. So in this system of agile data science, we value the document over the relation. This is, I used to live on a farm in outside Athens in Georgia. And this is, I guess after I moved away, I'm telling my dad to plant a cover crop to improve the soil, because we have really thin red dirt, Georgia red clay. And so you can see this email. It's a simple document. You're familiar with it. Well, this is the raw data of that, and it's actually very similar. This is the relational representation of an email. This is the Enron emails from the large scandal. And this is the relational database schema for it. And this is my attempt to recreate a document from that. And I didn't quite get it. I had to use a MySQLism. And I'm not the best person at SQL, but I feel like this is harder than it should be. And that if you're thinking in terms of this, you're really way off in terms of connecting with the data. And so I would suggest that relational data is a legacy format. Up to some limit, you can project. Storage is really cheap. So you can just do compute the result of the cubes and project that stuff to disk. You don't really have to do that on the fly, up to some reasonable limit, of course. You can duplicate joins into one big record type. Even if you duplicate fields, that's OK. Again, storage is really cheap. So you can ETL once on import, not every join. You don't do no joins, but you do far fewer. And then semi-structured documents preserve the data's actual structure, just like it was there in the email. And also with new column compressed formats and databases, you sort of get the benefits of a relational database without actually storing your data in a relational manner. Column compression is a wonderful thing. So we value imperative languages over declarative languages. In data science, you fundamentally don't know what you want to select, generally. You sort of have this data, and you're not sure about it, and you're cleaning it, and you're checking it out as you go. And it's an inherently imperative process. So SQL can work for this. You can do it stepwise, but it's not optimized for that process. And since 85% of your time, the statistic everybody makes up, but is spent munging as opposed to doing cool math, having tools that are optimized for this process is essential, which is, in the process, is iterative snowballing insight. There's also the opportunity with imperative languages to self-optimize and not rely on the magical query planner.
What's munging?
Munging is like ETL, like reformatting regular expressions to extract the column you want from the big blob of text that you get, that kind of thing. And so we value data flows over selects. This is a simple data flow. There was a tool called Pigpen that was research out of Yahoo that turned pig script into these charts. This one I've done manually, but it's a really great piece of research that now I think Netflix has done a newer web app-based version. But this is how you count the number of emails between people. So you do a little bit of ETL, you lowercase email addresses. You typically do ETL as you actually make the imperative queries. This is a longer example. So what I'm getting at is Hive is really popular because it's like a sort of data warehouse thing on Hadoop. You can get at data that's not very structured. It's very powerful. But for doing data science, I tend to value Pig over Hive for building analytics apps. Pig will eat anything. It's optimized for refining data as opposed to consuming it. It's imperative and iterative. It's data flows that are SQL-ish, but not SQL. But if you know SQL, it's easy to learn if you know a programming language. There's code modularization via macros and UDFs in many languages. And with pig streaming, you can stream through any tool, like R, for instance. And what it allows us to do is to prepare our data on Hadoop as it's going to be consumed in our application. So it gives us that consistency of data model throughout. That being said, if you love Hive, use Hive. Or Shark, or whatever. And so there's a requirement that's fairly absurd. At localhost level, on a sample versus petabyte scale, you want to use the same tools. Simplicity is scalability, so we want the highest level tools we can get. You can prepare a good sample with documents. It's very easy, as opposed to with relational data. It's kind of tricky because your joins will miss. Use pig local mode. Illustrate's a great command that helps you generate example data, even from a large data source. It'll sample and do some generation to satisfy, like if x is less than 5, it'll show you 4 and 6, and then 4 getting through. Run the stuff locally, get it working, and then run on the cluster and push it to your key value store. and skip object relational mapping. If the format the data is stored in is not consistent with the format that the designer ends up viewing and consuming it in, then you're really not on the same page. And why encourage that with a system that is designed to map between multiple abstractions? And so don't trust databases. Everything's recreatable from Hadoop at n equals 3. So you can trust data on Hadoop. It doesn't go away. But your database may crash. Who cares? Just rebuild it. And so Pete Warden kind of came up with this concept of the data value pyramid, where you start with just kind of plumbing records through. Then you start to make charts. Then your charts become interactive and link between different kinds of entities. That's the report level. Once you do that, you're sort of prepared to make predictions because you've learned about your data. And the goal of making predictions is to drive new actions that weren't possible before, and hopefully, if you're a capitalist, to capture some of that value. And so the simplest level we'll start with is just plumbing records through, which you want to do like even before your first meeting, hopefully. So you want to document, serialize your events. You can use protobufs, thrifts, JSON. I use Avro because it's optimized for large files. It has the schema on board, which is very convenient. So you can generate documents via relational ETL. This is using Pig to turn the Enron relational data into a document, which is not much longer than the query. You can serialize events from streams. So in the book, yeah.
So one pain point about Pig is how you manage the schema in your scripts all the time. Do you have any thoughts on that?
I tend to view that one of the problems with Pig is that you have to manage the schema in your scripts. And so I sort of view that as an asset in the sense that that's the place where the logic is happening, and so that makes the most sense to prepare the schema at that level. That being said, it can certainly be tricky to juggle a bunch of schemas, and yeah. Yes, so you can save any relation into Avro format and then load it later, and the schema will be persisted. You mean like if you store using Pig storage and the schema is like gone?
Yeah, and then there was hcatalog, but I know in its earliest incarnation.
Yeah, so there's two approaches. Avro is one and hcatalog is another to schema management. They're both probably good. But you do use Avro storage. There's a new one in Pig 12. Joe Adler at LinkedIn totally rewrote it. And so the old one is still in Piggy Bank, but the new one is a built-in. So try it out. So in the book, we download your Gmail inbox and serialize the emails as Avro documents. And so that's a common pattern for generating documents. You might also ETL logs. And so what you want to do is plumb these atomic events, like the lowest level thing that you're operating on in terms of data, through to the browser right away. So this is a stack that is kind of neat and cool that I've used. It's, you serialize events to Hadoop. Then you've got Mongo Hadoop project, which joins to MongoDB. Then you've got a node MongoDB driver, and you can get JSON out to your web app. That being said, I don't really care what stack you use. If you look at a bunch of the blog posts, we've done like a dozen different stacks, or half dozen. So all right, step one, cat the Avro serialized events. This is what an email looks like serialized as an Avro, which is the same way it looks in raw data or on your screen. So we load the events in Pig, describe the schema, it's still consistent. Now we illustrate events in Pig. So this generates some example data so you can see an example, which is helpful. Next, you publish the events to a database. In this case, that database is MongoDB. It's a one-liner. If you have data stored as Avros to get it into a MongoDB relation, there's this little script that does this. And using the Mongo Hadoop project, your data is just kind of there. It's kind of neat. So now log into Mongo and check your documents. They're still, again, consistent. Now you want to publish those events to the web. This is a Sinatra app. It's a Ruby framework. It's really simple for building web apps. I also use Python and Flask a lot. Pyramid seems to be the newer, cooler kid on the block. And so the JSON looks like this in a web browser. So you'll notice that there's like a one-liner to transition the stack. So you can append to an Avro file, and you can then load and store that into MongoDB, and then hitting MongoDB with a MongoDB driver, get your data out to Flask where you can render HTML or JSON or whatever. So what's the point of doing that? The point is that now the designer, the product manager, the data scientist, they can all actually work on the same, they're all on the same page, and they can all work against the same reality. So product managers tend to have sometimes harebrained ideas, especially in the analytics field. And so you can now have grounded talks about what is and isn't possible and where you're at. You'll see how ugly the data is. It's probably worse than you think, especially if you're ETLing from a relational database. The most common fields end up being like null, zero, NA, that kind of thing. Relational constraints aren't actually all they're cut out to be for many applications. But you have a ton of work to do, but you can ship early and often, and it starts to feel agile, hopefully. So the next step is wrap the events that you've published in your web app in Bootstrap, which is a project out of Twitter that gives you like a Web 2.0-ish container for your application without doing any work. It allows engineers to make stuff that isn't so distractingly ugly no one will look at it, which is a real great, it's like a breakthrough for me when I saw this project. So this is JSON, or it's actually Python, a Python email record put inside a Bootstrap application box thing. So this is what it looks like once you create some fields out of the JSON structure. It looks like kind of an email browser. So then you can prepare a list of links to sorted events. So you can make like an inbox list. This is how you do that in Pig. You can do this in MongoDB if you add an index and sort, but you might not have that ability if you were using like HBase or something. So you might have to prepare pages of sorted documents depending on your scalability requirements. So that looks like this when you present an interface, which looks a lot like your inbox. There's a neat trick here. The work that you did to list emails can also be used to display them if you do searches. And Elasticsearch is a really cool system built on top of Lucene. It's kind of, to me, the Hadoop of search. It's really easy to use. And so if you run, like locally, a copy of Elasticsearch, this is all the work you have to do to make your emails searchable, which to me is out of sight. And then you just use curl to query it. We do this in the book. You get incredible code reuse. It's neat. All right, so the next step, since we plumbed our records through, is to create simple charts. So this is an example of a data table and a chart. So always start with an HTML table, because it always happens to me that there are holes in the data. Like there was a 0 value, and you didn't actually project a 0, and it's empty. And so your charts look weird. Things like that always happen. So start with a table on general principle. NVD3 is a library built on top of D3. There are several of these. You can use them or not. The D3 examples are pretty good and easy to extend themselves. Make charts. When we do that, we're aggregating by properties and displaying them, and that's the first step in entity resolution. So we start extracting entities: people, places, topics, time series, group documents by entities, rank and count, publish the top related things, time series, fill a page with charts. This is how you display the top n of anything in Pig. It's fairly straightforward. This is how you could do a time series of anything in Pig. And so the stack ends up looking like this. You've got bulk storage and Hadoop, so you're doing batch processing in the back. Then you've got a document or key value store you're publishing to. Then you've got your application server client-side JavaScript. You might also have like a sub-real-time processing layer. This could be like Storm, or it could be queues and workers. So the point of this is that like anyone can contribute because the schema is consistent throughout at any level according to their talent, right? So the designer can mock something up in HTML and quickly get it plumbed with real data. Or the web guy can do it in JavaScript, or you can do it in Python, or in MongoDB, or in Pig, and everyone is unconstrained and able to be creative without sort of having to wait on anyone else. So that's great. Everyone gets to contribute new stuff. But we know that things scale most easily when we push them back into Hadoop, because Hadoop scales horizontally for a lot of processes. And so you want to gyro or ticket them for technical debt that they should be shoved back as you go. So this is counting the number of emails, how to do it in JavaScript, in Python, in MongoDB. Look, MapReduce, even in JavaScript, is very lengthy. So never write MapReduce if you don't have to. Use a higher level tool. And then Pig. All right, so the next level up is reports. So once you start linking these pages, you get like related email addresses, for instance. You start to get a reporty feel to your pages of charts. We start to extract entities from properties. We started to aggregate when we built charts in the last step. Each entity gets its own type of web page. Each unique entity gets its own web page with a unique ID. We can then link to entities as they appear in our atomic records. In this case, emails, an email address can be a link, that kind of thing. So we link most related entities together between types and within the same, do more visualizations, parameterize these results with forms. What we're doing is creating interactive ontologies of semi-structured data. A good way to start a user out in this application, other than search, is to do a tag cloud. But beware, so we've abandoned relational data, and now we may well filter the same data in two different ways during our data pipelines. Later try to join them, and we'll get key misses. So you'll go from this entity to that one, and it'll be 404 not found. It's a bummer when it happens. So what you want to do is, when you're filtering the base records, try to push those filters together into a single file that you then branch out from. This is something to keep in mind. So you're at the point now where you can get people clicking, learn from them, take note, Google Analytics, what people are actually using. One of the nice things, though, about this step is people will sort of tell you things that lead you to be able to generate insight. They'll be like, oh, well, I really want to see this, or I noticed this, or they'll help you clean the data, like, oh, this is totally screwed up, this field. And sometimes they'll even tell you how to fix it. So now we've done a lot of work, and we're in a position to make predictions and recommendations. So we've extracted entities, their properties, and relationships. Our charts show where our signal is rich. We've cleaned our data to make it more presentable. Everyone has an intuitive understanding of the data based on the work we've done so far. And they got that by actually touching the data and exploring it. So now we might start to think in different perspectives, like networks, time series, distributions, natural language processing, Bayesian inference. This is a network. Bob knows Sarah. Sarah knows Bob. Bob knows Sarah. Bob likes Sarah, but not too much. So this is the pig code to compute like a weighted network from your inbox. This is a visualization of my inbox. This isn't a good visualization, but I put it in here because you should always render a network for your project. You can make a network out of most anything. And you should render it in Gephi, which is really easy to do because it'll get your project funded. People like to go by these and they're like, is that a heart? You know, oh, the data is really complex and mysterious, and they sort of start to connect with the processes that you actually do, but it's kind of a picture of it. And so you can get people on board this way. So this is PageRank in Pig, so you can do social network analysis. I think we've already shown time series. you can like smooth sparse data, regress to find trends. There's a macro I did for TF-IDF, term frequency, inverse document frequency. So it's like a one-liner to call that process to work on documents at scale. Pig's really neat this way. So this is just a simple word count on the email I sent to my dad about planting a cover crop. It's a Wordle. Grass, plant grass, plant grass. It works. It's very simple, but there's also an example here for latent Dirichlet allocation. This is a man called Bayes who was incredibly naive. Bayesian inference is basically doing pivot tables and then a little trick at the end. So it's great if you're not that algorithmically advanced. And it tends to perform surprisingly well to the point that everyone is always trying to beat it with their sophisticated algorithms and often don't. And so the literature is mostly failing to beat naive Bayes if you want to look at it that way. But it's definitely a great technique to use. So let's look at doing something like that to recreate Gmail suggested recipients. This is me emailing. I had 2 editors. This was the first one. It tells me who I might want to include. So this is the code to reproduce that feature in Pig. We'll step through it. So you get a count from to how many people I email. So I emailed Mike 28 times. Then you get a co-occurrence count of to and CC field, and then divide that by the total sent to get a probability of inclusion. And then next, oh wait, that's actually how this feature works. It's, Google says simple algorithms, lots of data, and like this proves it. So now you can add predictions to your reports. The probability that my wife will reply to one of my emails is 0.13. We're going to seek counseling. But no, a lot of times I send her bills and things. But so we want to enable new actions. So why doesn't Kate reply to my emails? We have to do at this point some business analysis. I may not be catching her at the right time. We have those time series. So email pops in at the top of your inbox. So if someone is emailing a lot, that would be the time to send it to them. We could use that to optimize that process. Are my emails too long? Nobody replies to my opuses. They're just embarrassed that I wrote it. Are they meant to be replied to, or am I just forwarding existing emails? Are they nice? We could send them an analysis, which is a Bayesian thing. Do I reply to her emails? This was like a men are from Mars, women are from Venus moment for me. It was deep. I don't think I do. I think I I got that email, yeah. And then do I CC the wrong people? The probability that my wife will reply to an email where I include my mom is 0. So the book was up and on O'Reilly's open publishing system, and I had been blogging about this stack with Hadoop, MongoDB, and then a simple web front end. And a guy named Michael Baker in Australia started a company called Packet Loop, and he built a library called Packet Pig. And what he does full data capture on your internet connection. So he logs every single packet. Storage is cheap. You can generally afford to do this, even if you have a pretty thick pipe, because it's almost always not saturated for most connections. So he logs everything onto 3 or 4 terabyte disks, and then he hits it with on S3 with Elastic MapReduce. He wrote a library that hooks with Snort to do intrusion detection. And what he does, you may know that you're going to get broken into tomorrow by the bug that came out today, but you don't know if someone had that and they broke in last week. Well, with his system, you can go and scan the old data with the new signature and find out if they broke in, what they took, that kind of thing. It's really cool. And so he follows this process. He refines the data in Pig. He uses R in streaming, actually, instead of Python. But so he scans it, and it looks like this. So this is just grouping by country. This is some attacks happen to be coming from China. And so this is way cooler than anything I've shown. But the point is, this is not that much different. He had a designer and a web developer work on this for probably some weeks. And he was able to use this process to get something that actually looks like shippable. So that's it. By the way, I am currently interviewing, and so if you want to hire me, you think this stuff is great and you want me around, you can totally do that.
Wow, it's the first time in the
Thanks.